So say we have a real analytic, regular codimension 1 foliation of x equals the open unit square. And the leaves of the foliation are given by this. Now what we can do is rearrange this into a different form. And now we have an explicit, so we change y to phi s of x. Then this is explicitly written instead of the implicit relation we had above. Now let's look at this locally near a cone point, this foliation. So right locally, we have the picture here. More globally, the leaves, curve back around. And we can draw the same local picture for, say, Q over there. Now we must ask ourselves the question, what if we view this as the kernel of an integral transform? So we'll have to go to the next page to find out. So if we set this up, we get this, where f of x is our test function, phi s of x is our kernel, and f of s on the left-hand side is the image of the integral transform. We're obviously integrating over the unit interval here. Let's, for now, let's set f of x equal to 1. So that's just 1. So we're really integrating over our kernel. So we're left with this right here. Now we can relate this kernel to the Fourier, Mellin, and Laplace transforms. But the reason we're sticking with this particular coordinate system and this particular kernel is because we're working over a square region. Now this integral happens to equal 2 square roots of s, k1, 2 square roots of s, where that k1 is a modified Bessel function of the first kind with index 1. So basically integrating over the character itself gives us a k Bessel. Correction, I meant to say modified Bessel function of the second kind. So if we look at the Laplace-Beltrami operator in polar coordinates, and we look at this cone point locally, and the radial L2 decaying solutions turn out to be k Bessel functions after we solve an appropriate eigenvalue problem. Very intriguing indeed.